Hello everyone, my name is Teng from Rutgers University. Today I will be talking to you about research detailed in our paper titled Spatial and Temporal Splitting Heuristics for Multi-Robot Motion Planning. This is a work together with Shuai and Professor Jingjin. We studied the one-shot multi-robot motion planning problem on grid graphs. A typical setup for this MRMP involves a grid graph, a number of robots with start vertices and goal vertices. As shown in this figure, robot starts from red vertices and need to go to the green vertices. At each discrete time step, a robot may stay at its current vertex or move to an adjacent vertex. The task is to find collision-free paths for all robots. We consider two objectives to minimize respectively. The first one is max span, which is the time for all robots to reach the goal vertices. The second one is sum of costs, which is a cumulative cost function that sums over all robots of the number of time steps required to reach the goal. This problem is also called multi-agent pathfinding. The problem is a fundamental research interest, popular in industrial applications. It has been proved to be anti-hard to solve optimally. So our motivation is to design heuristics that can solve this problem efficiently without losing too much optimality. Next, let me introduce some related works. MRMP has been actively studied for decades. Reduction-based method is to reduce MRMP to other well-studied problems. One of the examples is to reduce MRMP to multi-network flow problem and then use LP solver to solve. The coupled approach, or like operation decomposition, CBS, and the ECBS, first find a path for each robot and then resolve possible conflicts and return a global feasible solution. There are also rule-based solvers like push and swap, push and rotate. The contributions of our work are listed as follows. We systematically explore split heuristics over the temporal and spatial domain. We propose the time split, space split, and the combination of both heuristics. We perform experiments showing that these heuristics can be used with standard solvers like ILP solver and ECBS solver. The heuristics can bring huge boost to the computation time, while the solution returned is still 1.x optimal. We designed two heuristics. Both of them are based on divide and conquer. That is, first we divide the original problem into several subproblems. We solve these problems separately and then combine the solutions. First, let me introduce the time split, which performs the split over time domain. We split original problem into k subproblems. In the first step, we find k-1 feasible intermediate states for all robots. Then we solve the resulting subproblems using standard MRMP solvers in general. After all of the subproblems are solved, we concatenate the path and evaluate the final max span or sum of costs. Here is an example of two-time split. To route the robots from red vertices to green vertices, we find yellow intermediate states. Then a original problem is divided into two subproblems. The first one is to navigate the robots from red vertices to yellow vertices. And the second one is to navigate the robots from yellow vertices to green vertices. How to find the intermediate states that can keep the optimality and make the algorithm as efficient as possible is important. First, we find individual paths, ignoring the intercollision among robots using A star in descent order by path length. For minimum max span problems, we split evenly over time domain. For each subproblem, the distance a robot will go is roughly the shortest path length over k if the split level is k. For two split, the intermediate states are the middle points. As for minimum sum of costs, MRMP, the max span version can be very suboptimal since the sum of costs of their subproblems are not additive. Look at this example. If we choose the intermediate states as the second picture shows, then both of the sum of costs in the first subproblem and in the second subproblem are 3. The sum of cost of the first subproblem is 3, and the sum of cost of the second problem is also 3. But the final sum of costs will be 7 instead of 6, because the robot must wait for one time step in the first subproblem. For minimum sum of costs MRMP, we let robot travel long enough in each subproblem so that robot can reach their goal as early as possible. In this case, the intermediate state for robot 2 is chosen here. Then the sum of costs in the first subproblem is 4, while the second subproblem has sum of costs of 2. The final sum of costs are 6, and in this way, the sum of costs are additive. We show that the time split heuristics can be applied in IRP solver and ECBS solver. First, we test time split IRP on a 32 by 32 grid graph with 10% obstacles, minimizing the max span. The starting goals are randomly generated. 2T is 2 times split for short, which means that the original problem is divided into 2 subproblems. With the time split heuristics, IRP solver can solve an MRMP instance with 300 robots, while the optimality ratio is below 1.1. Optimality ratio is used to evaluate the solution optimality. It equals to the max span of the solution over max span lower bound. Larger optimality ratio means that the solution is more suboptimal. And we also test time split ECBS on DAO maps, for example, OO3D. The scalability has greatly been improved. We also test the time split for minimum sum of costs MRMP and compare it with the max span version. For both of ECBS and IRP, the result shows that our proposed sum of cost version, though might be a little slower, it has much better optimality ratio. Using the max span version and split IRP as the dashed lines show, the optimality ratios are 1.5 to 2.0, and our total time version has optimality ratio no more than 1.2. Time split improves the scalability of MRMP solvers like IRP. However, time split IRP is still not applicable on large graphs. For example, a 128 by 128 grid with a few hundred robots. Theoretically, you can do time split as many times as possible to make the subproblem small enough. The solution would be very suboptimal. Not to say the overhead of creating subproblems also becomes expensive. Therefore, we develop space split heuristics aiming to solve large problems for IRP. Use 2 space split as an example to demonstrate the idea. Given an MRMP problem, first we choose buffer zone B1, B2, which are of zigzag shapes. Then the original problem is divided into G1, B1, G2, B2. In this figure, buffer zone B1 is the green area and the buffer zone B2 is the gray area. The original problem breaks into 4 subproblems. They can be solved in 2 phases. In the first phase, the first subproblem is on the red part plus the green part. And the second problem is on the blue part plus the gray part, moving the robots from start vertex to intermediate vertex. In the second phase, the buffer zones are flipped, and then the robots are moved from intermediate vertex to their goal vertex. As for the intermediate states, we search the buffer zone and found an unoccupied vertex that has the smallest f value, where f is composed of 3 parts. The first part is the sum of distance from start and distance from goal. The second part is used to ensure the subproblems have similar size so that the parallel computation resource can be fully utilized. While the third part is the vertex occupancy density function. This is used to avoid high robot density that may heavily affect performance of low-level solver. Our goal is to solve much larger MRMP instances where pure time-split IRP cannot solve. We combine the time-split and space-split. The combined heuristics is called space-time split. We use combined heuristics to solve large instances. We test the combined heuristics with different speed levels on 128 by 128 grid with 5% obstacles. For example, for ASAT means that we first divide the original graph into 4 subgraphs and then use 8 time split to solve the resulting subproblems. The figure shows that the combined heuristics enable IRP solver to solve hard instances where nearly 1,500 robots were 16 times speed. As the black curve shows, may fail and can only solve instances with 100 agents. And in figure 10, we test different size of buffer zone. We use different size of rectangular buffer zone from 4 by 2 to 10 by 5. To our surprise, using larger buffer zone, we are worsening the performance in general. The green one using larger buffer zone has nearly twice computation time as the blue curve that uses small buffer zones. In conclusion, we developed 2 split heuristics that can improve the scalability of MRMP solvers. Time split is complete and theoretically works for any MRMP solvers. Space split is not complete and only suited for large grids with small percentage obstacles. If there are too many obstacles, we cannot even find such buffer zones to make space split work. Currently, the buffer zone is chosen manually and is fixed in the entire process. As for future works, we would try to explore the possibility of automatically and dynamically choosing buffer zones that don't need to be of rectangular shape to make space split applicable on other graphs, as well as improve the scalability and optimality. That's all. Thank you.